Hey guys, in this video let's tackle about a regenerative Rankine cycle. But before we start, let's consider that we already know how to read the steam table and how to use the interpolation process. So let's start.
A regenerative Rankine cycle is a process where heat is taken from steam between turbine stages and used to heat water as it goes through pump stages. This is a regenerative Rankine cycle. A boiler, turbine, condenser, and two pumps, one open feed water heater with two closed feed hot water heater, and two traps. Point 1 goes to the turbine, and the point 2 from turbine to the closed feed water heater, and another point 3 to the closed feed water heater. Then the point 4 will go back to the boiler to reheat. Then when it comes out, it is the point 5 back to the turbine. Then the point 6 from the turbine to the open feed water heater. The point 7 is from the turbine to the condenser. Then when it comes out, we have the point 8. Then point 9 from the open feed water heater to the pump. Point 10. Then point 11. Point 12. Point 13 from the closed feed water heater back to the boiler. Point 14 from closed feed water heater to the trap. Then the point 15 from trap back to the condenser. Then we have the point 16 and the point 17 trap to the open feed water heater. So to calculate, let's have all the given. So before that, where H is equal to enthalpy, S is equals to entropy, U is the internal energy. To get the efficiency, we need to calculate all the enthalpy, entropy, and the internal energy from each point. So, point 1, we have a given pressure is equal to 2.032 megapascal, and the temperature 1 is equal to 232 degrees Celsius. So to get the value of A sub 1 and H sub 1, we have to use the interpolation process using the steam table. So A sub 1 is equals to 6.4431 kilojoules per kilogram, and H sub 1 is equal to 2853.4016 kilojoule per kilogram. So let's proceed to point 2. At point 2, we have a given pressure at 1.572 megapascal, and the A sub 1 is equal to A sub 2. Is it constant? So we have 6.4431 kilojoule per kilogram. So to get the H sub 2, we have used the interpolation process. So let's consider that we already know how to use that. So the H sub 2 is equals to 2800.65 kilojoules per kilogram. Okay, let's proceed to point 3. At point 3, we have a given pressure 1.061 megapascal, and the A sub 1 is constant to A sub 2 is equal to A sub 3. So A sub 3 is equal to 6.4431 kilojoule per kilogram. So to get the H sub 3, interpolation process again. So H sub 3 is equal to 2724.578. At point 3, we have a given pressure 1.061 megapascal, where S3 is equal to S2 is equal to S1. So S3 is equal to 6.4431 kilojoule per kilogram. In this point, we can get the value of X using the formula S3 is equal to SF plus X times the SFG. Since we have the value of S3 6.4431 and the SF is 2.1633 using the steam table, plus X times the value of SFG 4.4023, we can get the value of X, where X is equal to 0.97 or 97%. To get the value of H3, we can use the steam table, which has the value of HF is equals to 774.28 plus the value of X, which is 0.97, times the value of HFG, 2006.0. So H3 is equal to 2724.578. At point 4, we have a given pressure is equals to 533 kilopascal. So S1, since we already know that S1 is equal to S2 is equal to S3 is equal to S4. So S4 is equal to 4,431. So we need to find the value of H4. To find the value of S4, we need to get the value of X using this formula. S4 is equal to SF plus X SFG. Since we have already the value of S4, which is 6.4431, and the value of SF from the steam table, SF is equals to 1.88516 plus the value of X, which is the unknown, times the value of SFG from the steam table, 4.915. So the value of X is equal to 0.927 or 92.7%. To get the value of H4, we have the formula HF plus X times HFZ. So H4 is equals to, since we have already the value of HF from the steam table, HF is equal to 650.124 plus the value of X, which is 0.927 times 2110.84. So we can get the value of H4. H4 is equal to 2597.60. So let's proceed at point 5. At point 5, pressure 4 is equal to pressure 5. So pressure 5 is equals to 533. Just copy the pressure 4, kilopascal. So H5 is unknown. The H5 is also unknown. So using the interpolation process, we can get the value of H5. H5 is equal to 2794.78. Then the S5 is equal to 6.9457. So let's proceed at point 6. Point 6. At point 6, the pressure is given, which is 227 kilopascal. And we already know that S3 is equal to S6. 6.90457. So to find the value of H6 is the unknown. So we have to get the value of X first, since we have already the value of S6. So S6 equals to SF plus the value of X times the SFG. S6 equals to 6.90457 is equals to, since we have already the value of SF from the STEM table, our SF is equal to 1.57364 plus the unknown value times the SFG from the STEM table, which is 5.5113. So X is equal to 96.7% or 0.967. So we can get the value of the H6 using the formula HF plus X HFG. H6 equals to HF from the STEM table. We have the value of 524.93 plus the value of X, let's put 0.967 times the value of HFG, which is 2195 or 21.905. So S6 is equals to 2640.14. So let's proceed to point 7. At point 7, we have a pressure 54 kilopascal. Then the S5 is equals to S6 is equals to S7. So S7 is equal to 6.90457 for 5 mn. So HF is equals to 348.50 from the table, and the HFG is equal to 2300.52. So we can calculate the value of X using the value of S7. S7 is equal to SF times plus the value of X times SFG. S7 is equal to 6.9457 is equals to SF, which is 1.11364 plus the unknown value times the SFG, which is 6.434. So X is equal to 0.897 or 89.7%. So using this value, we can get the value of H. So H7 is equal to HF plus the value of X times HFG. So H7 is equals to HF 348.53 plus the value of X 0.897 times the HFG, which is 2300.52. So H7 is equals to 2412.1. At point 8, all we need to get is the H8, where H8 is equals to HF at point 7. So H8 is equals to 248.53. So in this point, we can get the value of the work pump 1. Then the work pump 1 is equals to volume times pressure 9 minus the pressure 3. So let's input the value of the volume from the steam table, which is the 0.00103128 times the value of the pressure 9, which is 277, minus the pressure 3, which is the 54. So work pump 1 is equals to 0.1784 kilojoule per kilogram. So let's proceed at the point 9. Point 9 is this work pump is equals to H9 minus H8. To get the value of the H9, since we have already the value of the work pump, which is 0.1784 from here, then H9 is the unknown value minus the value of the H8, which is the 348.53. So the H9 is equal to 348.7084. At point 10, all we need to get is the H10. H10 is equals to HF at the point 6. Then the mass 1593. Work pump is equals to volume times pressure 11 minus the pressure 10. So work pump 2 is equals to the volume is equals to 0.001130885 times pressure 11 is 160 minus the pressure 10, which is 277. So the volume is equals to the work pump 2 is equals to 1.5074. So to get the value of the volume 9, we can use the interpolation process. So let's proceed to point 11. So at point 11, we already know that the work pump 2 is equals to H11 minus H10. We have already the value of the work pump 2, which is 1.5074, is equals to the unknown value minus 521.93. So H11 is equals to 53.4374. At point 12, where the H12 is equals to HF at point 3. So H12 is equals to 774.36. Point 13, H13 is equals to HF at point 12. HF at point 2. So H13 is equals to 854.94. At point 14, we have H14 is equals to HF at point 3, where H14 is equals to H15. So we get the value of H14 is equals to 774.36. Then H14 is equals to H15. So the H15 is 774.36. Then at point 16, we can get the value of H16, where at HF at point 2, we have 854.94. At point 17, we have the value of H17 is equals to 854.94. So at this point, we should get the value of the masses. We will consider that this one is the closed feed water heater. There's a tube which has the enthalpy and the mass. Let's use the energy balance, which is mass in is equal to mass out. So H2 times M2 plus H12, which is coming in, is equal to the coming out, which is H13 and the H16 times mass 2. So From algebraic method, we can get the value of mass sub 2 is equal to 0.04. Then, from the another closed feed water heater, the same process, mass in is equals to mass out. Then the mass 3, we can get the value of mass 3, which is 0.13. From the open feed water heater, the same process, mass in is equals to mass out, we can get the value of mass 6, which is 0.07. The same from the condenser, so we have the mass total, which is 0.76. So we can get the value of the work turbine 2, which is equal to enthalpy 1 minus the enthalpy 2, which is 2853.40 minus 2800.65. So we have the work turbine value 52.15 kilojoule per kilogram. So in order to get the 2 work turbine, then the work turbine 3, we have a formula 1 minus mass 2 times the H2 minus H3, then substitute the value, we can get the value of 73.04 kilojoules per kilogram. Next, we have to get the value of work turbine 3 and work turbine 4, which is comes out from the formula 1 minus 2 times M3 times H3 minus H4, which is 105.4 kilojoule per kilogram. And from the work turbine 5 and work turbine 6, you can get the value of 128.35. From the 6 work turbine and the work turbine 7, we have the value of 173.31. So from the work pump 1, we have 1 minus mass 2 minus M6 times the work pump 1. So we have the value 0.9588 kilojoule per kilogram. To get the value of the work pump 2, we have 1 times the value of the work pump 2 is equal to 1.507. Next is the heat added is equal to H1 minus H13. So we have 1998.46 kilojoule per kilogram. Then from heat added 4 and heat added 5, we have the formula 1 minus mass 2 minus mass 3 times H5 minus H4. So we have the value of 163.66. Then to get the value of the total heat added, so let's add all the heat added. So we can get the value which is 2162.12. So from using this value, since we already get the work net, so we can get the efficiency using the formula NTH is equals to work net over the heat added total. Work net is equal to work turbine total minus the work pump total. So since we have already this value, so let's substitute, which is 532.84, the value of the work turbine total, and the value of the work pump total is 1.6658 over the heat added total, which is 2862.12. So the efficiency, overall efficiency, is equal to 0.25 or 25%. That's all.